Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, New St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, New St. Augustine.
Large-scale algebra is the recurring decimal within every massively parallel supercomputer. My father, Nnameka James Emeagwali, began teaching me how to solve the quadratic equation of algebra. I learned the quadratic equation in mid-1964 and at age 9, and from the algebra textbook that was written by an English schoolmaster named Clement Vavasso C.V. Durrell. I learned the quadratic equation in our house along Benobar Street, Abo, Nigeria. Fast forward a decade from Benobar Street, Abo, Midwest Region, Nigeria, to 1800 Southwest Campus Way, Corvallis, Oregon, in the Pacific Northwest region of the United States, and to June 20, 1974. I was a 19-year-old that was programming a conventional supercomputer. Back in December 1965, when I was still in Abo, Nigeria, that supercomputer in Corvallis, Oregon, was rated as the world's fastest supercomputer. It was called the first supercomputer because it was the first supercomputer that could execute 1 million instructions per second. I programmed that supercomputer from teletype machines and in BASIC and Fortran languages. Fortran was a general-purpose, high-level, that is, natural and third-generation computer language. Fortran is the acronym for formula translation. BASIC is the acronym for beginner's all-purpose symbolic instruction code. BASIC was a child of Fortran and was invented in 1946. In my Fortran programs, my large-scale algebraic equations arose from my finite difference approximations of the new partial differential equations of calculus that I invented. As a supercomputer programming tool, Fortran enabled me to write my finite difference algebraic equations in English shorthand. Back in 1974, I was supercomputing from a teletype machine and punch tapes, and doing so from Monmouth, Oregon, United States. In 1975, I was supercomputing with a deck of Fortran cards in Corvallis, Oregon. In 1979, I was supercomputing from JCL punch cards and supercomputing in the Foggy Bottom neighborhood of Washington, D.C. The term JCL is the acronym for Job Control Language. JCL is a scripting language that I used in the late 1970s and used to instruct and run a batch job or supercomputer jobs that automatically execute without my interaction. I used JCL to submit my supercomputer programs for execution in batch mode. I wrote my large-scale computational fluid dynamics codes of the 1970s and 80s in Fortran, a language that was invented 2 decades earlier and back in 1957. Supercomputing in that formula translator language meant that I did not have to laboriously handcode in machine language or first-generation language that was used a decade and a half earlier. I compiled Fortran into an executable language. In 1974 and earlier, many supercomputer programmers were trained as a mathematician. In 1974, I thought of myself as a pure mathematician who loves to program supercomputers. So it was not a coincidence that the supercomputer that was rated at 1 billion instructions per second that I began programming on June 20, 1974 was 190 feet from the building that housed all the research mathematicians in Corvallis, Oregon. My contributions to extreme scale algebra is the reason I see myself in algebra textbooks that are published in the United States and Brazil, rather than in algebra textbooks used in my country of birth, Nigeria. In Africa, white scientists became role models for black students, but rarely vice versa in Europe and North America. In the United States, I am taught as a black scientific role model to white children, but in my country of birth, Nigeria, only dead white male scientific role models are taught to black children. As a result of these centuries-old and well-orchestrated misrepresentations of how a genius should look, these African children grow up as adults and are shocked when they attend my scientific lectures and are surprised by the reality that the name Philip Emeagwali is cross-listed and on the same page with names like Galileo Galilei, Isaac Newton, and Albert Einstein. People that compared my lectures posted on YouTube to those of Albert Einstein are shocked to learn that I know more about mathematical and computational physics than Albert Einstein did. Research scientists are shocked by the extent of my scientific knowledge and that I have a deep understanding and a masterly command of materials. The black historical figures that are studied in secondary schools in Africa were the great kings of the West African Mali Empire that was founded in 1235 and dissolved in 1400, and the Songhai Empire that was founded in 1430 and dissolved in 1591. Other African historical figures that were studied in schools across Africa include the early 14th century king Mansa Musa and the mid-19th century Hausa warrior queen Amina of Zaria and the late 18th century South African warrior King Shaka Zulu. The late 20th century African history shifted from exploits in battlefields to the fight against apartheid in South Africa that was led by Nelson Mandela. I believe that by the mid-21st century, African history will shift towards contributions made by Africans in the continent and in the diaspora and made to human progress. The most important contributions that Africans can make include discoveries and inventions that will expand the body of human knowledge and that will make planet Earth a better place for all beings. I am the subject of school inventor reports because I contributed to the development of the massively parallel supercomputer. The parallel supercomputer demanded more from its inventors. I had to have an intimate understanding of the locations of every processor that outlined and defined my ensemble of 64 binary thousand processors. I had to have a deep understanding in 16-dimensional hyperspace of how to message pass my 2 raised to power 16 initial boundary value problems of mathematical physics and how to email the associated codes across my 16 times 2 raised to power 16 or 1,048,576 bidirectional email pathways, and how to route my 64 binary thousand emails to my 16-bit long email addresses. Each email address had no @ or .com suffix. In June 1974, I was programming a conventional supercomputer and using the machinery to sequentially solve a system of linear equations of algebra. Fast forward 15 years to the 4th of July 1989. I became the first person to figure out how to harness a new internet that is a new global network of 64 binary thousand processors, and how to use those processors to cooperatively and simultaneously solve a grand challenge problem that is otherwise impossible to solve. An invention only occurs when its inventor crossed a boundary of human knowledge and that had never been crossed before. For me, Philip Emeagwali, I crossed into the never before understood frontier of knowledge of the parallel supercomputer that is the world's fastest computer. I was the first person to cross that frontier, and I crossed it at 8:15 in the morning of July 4, 1989 in Los Alamos, New Mexico, United States. Shortly after my parallel supercomputing discovery, the news headlines became African supercomputer genius wins top US prize. Without parallel processing, the supercomputer of today will not exist. I was in the news headlines because I discovered how to solve the toughest problems arising in STEM fields. I discovered how to solve real-world problems and how to solve them across a new internet that is de facto one seamless cohesive machinery that is a virtual supercomputer. My quest for the fastest supercomputer that will compute across a new internet that is a new global network of 64 binary thousand processors began on June 20, 1974, and began as a science fiction and as a theory or an idea that is not positively true. My supercomputer quest began in a singular central processing unit that was my metaphor for the computer, and that was a mere acorn or the seed of an oak tree. By the summer of 1974 and at age 19, I was only mentioned twice in newspapers. First, in a newspaper in Nigeria, and then in the United States. The name of a 17-year-old Philip Emeagwali first appeared in 1972 in the science column of the Daily Times of Nigeria. The photograph of a 19-year-old Philip Emeagwali appeared on the cover of a local newspaper that circulated in the cities of Monmouth and Independence, Oregon, United States. That Oregonian newspaper article was published within 6 days after my interview that occurred on August 9, 1974. Taking a retrospective look, my quest for the fastest supercomputer began on only one central processing unit that was my metaphor for an acorn or the seed of an oak tree in the United States. My acorn blossomed into a mighty oak tree that was my metaphor for a never-before-seen internet that's de facto a supercomputer. That new internet was a new global network of 64 binary thousand tightly coupled and identical central processing units. Each processor operated its own operating system and shared nothing with its 16 nearest neighboring processors. Looking back to the mid-1970s in Oregon, United States, I was coming of age and growing in my awareness that abstract equations, whether algebraic or differential, must be used to discover and recover otherwise elusive crude oil and natural gas, and recover them from the mile-deep oil fields of the southeastern region of Nigeria. Mathematics is the invincible and abstract weapon that is used to fight poverty in Africa. My quest for the fastest supercomputer took me from the first supercomputer that could execute 1 million instructions per second that was at 1800 Southwest Campus Way, Corvallis, Oregon, United States, to an ensemble of 64 binary thousand commodity off-the-shelf processors that was in Los Alamos, New Mexico, United States. In the 1970s and 80s, I was a researcher in search for the massively parallel supercomputer that I hoped will become the world's fastest computer. In theory, the grand challenge question was this: how can we execute infinite calculations and do so across a large but finite number of processors, or across an internet and complete it in finite time? The answer is that it will always be impossible to execute infinite calculations. But in 1989, I was in the news headlines because I discovered the practical answer to that grand challenge question. Namely, I figured out how we could reduce 180 years or 65,536 days of time to solution across a new internet, that is a new global network of 65,536 processors, that is not a supercomputer per se, but that is a new internet de facto. An important problem that takes 108 years of time to solution is classified by the US government as a grand challenge problem. That grand challenge problem is solvable in 108 years, but is unsolvable in one day. In 1989, I was in the news headlines because I discovered how to reduce that time to solution from 108 years on one computer to just one day across a new internet, that is a new global network of 64 binary thousand processors. The reason I was able to solve the once impossible to solve problem was that I asked basic questions about how never before seen supercomputers could compute extraordinarily fast and apply that speed to solve the toughest problems arising in STEM fields. I discovered that the modern supercomputer must parallel process across millions upon millions of processors and must do so to solve as many initial boundary value problems of mathematical physics. In retrospect, it's incredible that parallel supercomputing, the vital technology that was mocked, ridiculed, and dismissed as a huge waste of everybody's time, is now benefiting everybody. Parallel processing, or solving many problems at once, is the irreducible essence of the modern supercomputer. In the 1970s, the parallel supercomputer was mocked and ridiculed and dismissed as useless and clumsy. That was the reason I conducted my research, my parallel supercomputer research alone. I programmed supercomputers alone because it was believed that it will forever remain impossible to harness an ensemble of 8 or more processors and use it to achieve a speed increase of a factor of 8 or more, and achieve that speed increase when solving the toughest problems arising in mathematical physics. Parallel processing was dismissed as the end of the road in the never-ending quest for the faster supercomputer. After my discovery that occurred on the 4th of July 1989 and that made the news headlines, the modern supercomputer that is the world's fastest had to parallel process across millions upon millions of processors that shared nothing. What kept me moving forward and alone? During my parallel processing research that I did in the United States and did in the 1970s and 80s was my visceral feeling that the computer is older than myself and that the supercomputer is larger than myself. On the 4th of July 1989, I discovered how parallel processing makes the supercomputer super. Parallel processing is vital to the computer and supercomputer. My contribution to the development of the supercomputer is this. I figured out how to harness the fastest massively parallel supercomputer ever. That discovery of parallel processing is used every day in every supercomputer. Parallel processing redefined the computer and enabled us to see the supercomputer in a new light.
Insightful and brilliant lecture.